Right. So welcome back again. So let us start today's session. Right. So let us have some introduction about this introduction to rotating DC machine. Rotating DC machines. Right. So in the last sessions we were discussing about the electromagnetic energy conversion, and we talked about, let us say, electromechanical energy conversion, EM energy conversion principles. So we deal in this three domains: electrical, mechanical, and the intermediate domain is magnetic domain. So in this process we were mostly coming across the electrical, mechanical, and the magnetic domain. Magnetic domain, and these two may be, one may be input, other may be output. So it can be either input or output, and this also can be either input or output, whereas this is the intermediate domain, which is a magnetic domain, in which, so we will be talking majorly the stored energy. So in specifically we will call this as stored stored field energy. Stored field energy, and here we would like to represent that as the stored field energy as WF. WF. This also can be represented as WF dash co-energy, which is generally equal to 1 by 2 into mmf, that is Fm, into the flux, mmf into flux, mmf into flux, or this can also be equal to half Li square if we know the current. And so in order to see the force developed by this field energy, so we'll be differentiating this with respect to the displacement. So dwf divided by dx or dg. Here dg is the gap, air gap, air gap variable, air gap variable, which is very important, air gap variable. And after this we were discussed about the two important parts of the machine, rotating machine. One is the stator. One is the stator. We said that stator does not have any moving parts. So and here we stated these things as, like, stator has, it has projected poles, projected poles, projected poles on the stator core, on the stator core. I was saying that, so stator and rotor is a core coil assembly. This is a core plus coil assembly, core and coil assembly, which is nothing but a magnetic circuit. So it has a core coil assembly in which on the core we will have some projected poles, where these projected poles on the stator so are generally helpful. So for the or okay, so let us say it has projected poles. Now what we would like to say here is that, so these projected poles are excited, or these projected poles are housing 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 coil coil coil, which which is is excited by, which is excited by DC supply. Let us say DC supply, as because I am talking about now DC machines. So it is DC supply. So now as a result, what happens when the coil is excited by DC supply, that entire structure will become the electromagnet. Just let me show once again that part, that what we had seen previously. So for which, so let me take a circle, let me choose the black color. So a circle, and here, so let me make the core structure, core structure core structure as like this. So this is what the core structure. So let's see that this is very much helpful in drawing the regularly. We will be drawing this kind of core structure, and this pattern let me draw a little bit better way. So here is our core structure, and now let me place one more circle a little bigger than this, and see that how I will be placing on top of this, which forms complete stator structure, stator core, and in which, so now let me remove this portion and this portion. So now see that it is, I had shown you in the last session also, that this is what the stator core, stator core. This entire thing is the stator core, stator core. Now where do we place the coil? The coil is placed on the projected poles. What are the projected poles? So see here, these are the projected poles. This and this one are the projected poles, projected poles. Now on these projected poles, we would like to place the copper wire. So how we place? Let us say in this way. So this is the starting terminal, and that will be going from the bottom and top over here, and from the top it is extended over here. Either you can extend from the top or bottom, it's your wish. So now, so what happens is that, so the flux should be flow from north to south. That means if this is becoming the north, then the flux direction should be in this way. So here also we should make the coil in such a way that, in such a way that the flux is from left to right. So how can I place the coil so that the flux will be left to right in this projected pole? Is from the bottom to top. Just cross check it, from the bottom to top like this. Now if the current is flowing through this, if the current is flowing through this coil in this way, this is downside, so apply the Fleming's right hand thumb rule. So then the current is flowing in this way, again upward. So if it is upward, no, it's not meeting the requirement, then let me make this to be as, this to be as, so slightly different, that from top to bottom. So this should be from the top and it is going to the bottom, and it is from the top it is going to the bottom, and from the top let me brought out, and it is coming over here. See this? So that is the, like, we should have sense that, so in what way we should make the coil arrangement, so that, so one side will be the flux is coming or emanating, other side is terminating. So that we need to, so means understand based on the experience, like this is, so downside current, so then it is coming out and going in this way and meeting over here. These are the voltage, DC voltage where we can apply. Now see that as the coil is in this way placed on the stator projected poles, so wherever the flux is coming out, so this is the terminal where the flux is coming out. If you apply the Fleming's right hand thumb rule, so the flux lines will be in this way. This is what the flux phi, and how the flux will flow in the stator core is that, so it will always choose the low reluctance path. So the core is having the lowest reluctance in comparison with the air. So now this entire thing is the core, and after reaching here this entire flux phi, it will be encountering two paths. One path is upside as like this is the core path where flux will be flowing. Other side also same, half of the flux will be flowing. So on the other side, this is what the stator flux path. So this much you should understand about the stator. And one important thing here is that it is easy to understand that it is easy to understand the nature of the exciting coil, this coil, and how it is placed. So one more thing just we will be regularly showing that is or I'll show that later on. So now let me talk about the rotor part. We said rotor has two different kind of thing. One is salient pole rotor, another is cylindrical rotor. Now let me consider the cylindrical rotor. So rotor structure. So I'm not specifically saying as a cylindrical or what, but just it is understood based on the construction what kind of rotor is the given one. So let us say I have a rotor. So with this thing, and just I would like to remove some portion of it. So prior to that, let me represent certain half circle of this entire arrangement. Now in this half circle, I would like to construct the rotor slots. So how? So as like this, let us say in this way, this is one slot. I said that we will be taking the side view or the two-dimensional view. So these are the slots where conductor is housed or placed. So these are the one more slots. See how many slots are there? 1, 2, 3, 4. So similarly on the other side also let me place 4 slots. 1, 2, and 3, and 4. These are the 4 slots. Now let me remove this part of the so yeah, so this part of the things, so that it look like real slot where we can put the conductor. Just remove these things, this and this. Now you can see that this is a cylindrical rotor where, so here we can place the conductors. So that this rotor core, so let me say this is the core of the rotor, one thing, core of the rotor. So this can also be called as armature hereafter. So try to understand this. This rotor core can be called as a armature. Armature. Now what does it has? It has slots. This is what the slot position where conductor is placed, means one kind of gap where we can insert the conductor. Clear? So it has a slot, and this like upper side it look like as a teeth, real teeth also. So this we call as a teeth, slot teeth arrangement. So armature has slots and teeth. Armature has slots and teeth. So this I am showing only the upper side view, or this project means general side view. So really how does it look like is that, so this may be extended something like this. This also may be extended like this. This is what the slot where we can place the conductor. And similarly here also it may be extended in this way. So this also may be extended like this. So see, where do we place the conductor? Conductor is placed over here. This is what the position in which the slot, so where conductor is housed. Similarly here also a conductor is placed, and here also a conductor is placed as like this. It will be going through that. So this is what the rotor slot and teeth arrangement. Slot and teeth arrangement. Clear? So just try to understand that rotor has armature. And how does it look like is that, so slot and teeth arrangement, there will not be any direct conduction between one slot to another slot, between one slot to another slot. So this understanding is also very important, so to know the electrical machine operation. So let us say here this is the center. So in this way you assume that the 3D view, so it may be extended something like this, and this also extended in this way, so like this, and this is other side of the rotor, and here also these may be extended in which the conductors are placed. So now we have dealt some more things also. Instead of representing conductor every time as like this, just let me place here, so right here. So if the conductor is placed as like this, as like this, so as like this is one conductor where current is going into the board as like this. So this is equivalent to, this is the position here. If somebody is looking, so here if somebody is looking over here, so then how does it look like? It look like a circle, means conductor equivalent. So inside that we represent the cross mark. So this is what into the page, means into the board here. So the current is going into it, into, current is entering. So whereas other situation, that if the current is in this way, it is coming out of the board, if it is in this direction visually. So here at this position, how does it look like? It look like a dot, the arrowhead going to be visible over here. So that we will show as circle inside that dot, which represents current is coming out of the board, current is coming out. So these are the general representation. Hereafter, instead of representing this entire conductor, just if current is entering into the conductor here, so as like this, so let me show here, if current is flowing into it, so here in this slot, just like here, let me say here, this is equivalent to, so one slot is there as like this is one slot in which a conductor is placed. This is the conductor, in this slot we have a conductor where current is going into it. So this entire 3D view can be just simply placed as a slot, inside that a circle in which the cross mark, which represents here this conductor is extended in this way, and where current is going into it in the same way. So here also we have one slot. Let us assume that current is coming out in this direction, the current is coming out. So here, so this is equivalent to, so we have a slot, as like this is what the slot, and this is other side. I am showing only one slot in which we will place one circle in which a dot is placed. What does it mean? This slot is holding a conductor in which current is coming out of that conductor, so towards us. So this is the generalized representation hereafter, so that you should understand. Okay. So now let us consider a two pole structure of the machine. So that what we had seen just now. So let me take again that, so the stator structure and the rotor structure. This is the stator poles. How many poles are there? Two poles. So sometimes we may have more than two also, that we will discuss soon. So these are the stator poles. Okay. So now let me place a circle. How I will place is that, just I want to make this to be fit in this. So just, yeah, so is it looking like proper core, right? So both side equal in length, right? So now let me place one more circle. So now this construction usually takes some time. So next time onwards I will come up with ready drawn diagrams, right. So now this is complete stator core. Stator core is completed now. So what I will do is that I will remove this portion. See this. So I will also remove this portion. This is what the stator core. Let me complete this section. This is the stator core, complete stator with the projected poles. And as I told you, instead of putting the coil and wounding around this thing, what I will say is that here we have a conductor, here also we have conductor, coil, and that nature we would like to show in this way, that if the current is entering over here, dot, here also dot, means current is going into it, here current is coming out from the bottom, cross mark. And see that if current is going into it, so place the fingers so on top side and hold it, or coming out, this current is coming out, so bottom to top. So use the, just otherwise, so let me give you, so one second, here the things will be like this, let me show. So the current is going into it, so let me extend this wire as like this. So it is going into it from where, from bottom and to top, and it is coming over here, and it is still coming out. So this is what the conductor as like this. Just I am showing the conductor. Now see that if the current is in this way, current is going, see current is going here, how does it look like? Arrow. So cross mark. So arrow look like cross mark. So here it is coming out. So how does it look like? As a dot. That is the meaning. So if the coil is placed exactly in real time like this, blue color one wire, so how do we represent those things is, this is the way of representation. Here current is going into it, where here is current is coming out of it. So let me extend this wire further over here, and again place the coil over here by the circles, and here again the flux should be in the downward direction, the same way is applicable over here. Then this is coming and connecting over here, and from this it is coming out, and let me brought out completely and placed over here, and placed over here, and the current is coming out of this. So it is entering here into the board. How should I show this? I should show this as a cross mark, and current is coming out of this terminal. How should I show this? As a dot mark inside the circle. So next is same thing, here the dot mark, here cross mark. So these things you should, these are minute things, but you should understand very carefully. So every time I may not explain all these things just directly, I will go with the representation. Okay. So this is one thing, that every time we will not show this blue color conductor, just instead of that we will show with this circle and dot cross marks, that's all. Okay, right. Now let me show for the core of the rotor. So for which let me take the circle again. So this is the rotor core, and let me make more circular form. So these are the, right. So now let me put this into some slots, just I'll show some sample slots. So it is cut into some slots, right. So now let me remove this portion, look like this. These are the slots where conductor is placed here, circle, circle, circle. Here conductors are placed. In the same way, this side also that slot arrangement will be there. Just as a sample, I am showing only this section. So let us say current is coming out of these conductors. So I'll show dot. I'll show as a dot. What does it mean? The current is coming out of that conductor. So where in this slot that corresponding conductor is placed. Clear? So this is the two pole machine. Two pole machine. So try to observe here. So the starting terminal of the coil, the starting terminal of the coil which is carrying a current of I amperes, we call as F1 field terminal, field coil current IF, and its terminals are F1 and the ending terminal is F2. So F1, F2 are the field coil terminals. So that thing can be shown as like this. So here simply a coil will be imagined as like this. It has two terminals, it has two terminals, starting one is F1, ending one is F2. This is what the field coil, field coil. Sometimes when we were showing the machine construction, directly we may show field winding which produce the flux. So how the flux is produced here? That flux will be flowing from north to south in this direction, as this is the north, this is the south. And how the flux path will take place? So the flux path through this core and it crosses this air gap, then it passes through the rotor core, then again it crosses the air gap, then again continues to flow through the stator core, then it split into two parts. The flux will be, half of the flux will be flowing in the upper side and remaining half of the flux will be flowing in the lower side. This is the flux path distribution in the DC machine. When we excited the stator coil, which we call as a field coil hereafter, stator coil we call as a field coil. This is what the stator coil, stator coil we call as a field coil, and which is carrying a current of I amperes. This try to produce a flux of phi. This is producing a flux of phi, which we call as a field flux, field flux. Clear? Right. So now some important thing, just let me show in this way that so the stator part is so simple that it nothing, just like a stator, which is a stator core and a coil. So the coil arrangement is so simple. It has only starting terminal, ending terminal, and one coil here. So for a two pole, so this coil is directly joined in series. Half of the segments are here, half of the segments are here. But so let us elaborate this rotor part and rotor conductors, how we place the rotor coil. Clear? So now let us see the rotor part. So for which just I would like to take some portion, that some portion of the rotor. So let me take this as a rotor, and now so in this rotor, first let me split that rotor into like a slot arrangement, slot teeth arrangement, slot and teeth arrangement. So for which, so let me carefully take these slots and teeth arrangement as like this, slot and teeth arrangement like this, etc. Okay, so here also we will have the slot and teeth arrangement and so on. This will continue, this will continue. Now so what I will consider is that some kind of diagram. So for which first what I will do is that, so let you have to imagine in this way, these things are extended in 3D view. I had shown you in the last session the real time rotor core. How does it look like? So this will look like this. and this also further extended, so we could not see that, but here I can extend. These are what the rotor slots. Up to this we could able to visually see this. Okay. So now what happens is that just let me place some conductors inside this. So how we place inside these conductors is that, let me consider one conductor here and one more conductor on downside. What does it mean? Here it has two conductors. This is one conductor, a solid bar, let us say iron bar kind of thing, and below that one more conductor is placed. Below that one more conductor is placed. Similarly, so let us consider. So this conductor, or initially let me take only one conductor, or your wish. Let us say this top conductor. This top conductor is going to be connected on the other side conductor, where the conductor is placed in some other slot. Here one more conductor is placed. This is a solid bar conductor, and these will be joined with a wire, again with a wire. Now if you see this, let us say this top conductor and this top conductor. So let me extend this wire just further as like this. This is one terminal, this is one more terminal, one more terminal. And if you see this, how these conductors are framed. So basically the conductors are framed in such a way that it has multi-turn conductors as like this. Let me take one conductor here. This is one conductor. So this is one conductor, and one more conductor let me choose over here. Now how I will join these conductors is that with certain other wire as like this. So I will be joining these conductor by the special some wire piece, and this is the starting terminal. Let us say S1, starting terminal is S1, ending terminal is finishing terminal F1. So this is S1 and the ending terminal is this one is F1. So if you observe, so this red color one is the active conductor. This is what the conductor, and this is also a conductor. How many conductors are there here? So only this side one conductor is there, on the other side one more conductor is there. So this kind of arrangement we call as a coil. This is called as a coil. So coil consists of two things. So this is one side of the coil, so coil side 1, and this is other side of the coil, so coil side 2, coil side 2. So a coil consists of two coil sides. In each side we may have one or more than one conductor, let me write that point also. Each side of the coil, each side of the coil each side of the coil may have may have may have one or more than one or more than one conductor. If it is one conductor, we call single turn coil. So here specifically this is, so more specifically we can say that this is a single turn coil. And usually to get more induced EMF or more torque, we take multi-turn coil. How does it look like? Let me show that. So here let me choose two conductors, one conductor here one conductor here, sorry, it's not good. So and one more conductor beside it, two conductors, and the other side again two conductors. So now let me make the connection diagram as like this. Let us say this is the starting one, and this is what the S1 starting terminal, and the end of this side conductor is extended with a wire, and that is connected to other side of the conductor, and this end of the conductor will be extended further, and it is joined to the second conductor in the side one, and this will be continued and like this. So it will be connected to the next conductor and like this. If one more conductor is there, we will try to connect it. Let me take third conductor also here. Here also third conductor. Three conductors in each side. Now how I will place? So this also will be connected over here, and this will be extended further, and it will be connected to third conductor in side 2 and so on. The last one will be brought out. That is what the finishing terminal. Finishing terminal F1. So this is what a multi-turn coil. Multi-turn coil. See that how we placed, how we made this multi-turn coil is that, try to observe. This is one side. This is one side of the uh, conductor. Let us say coil. This is one side of the coil. This entire thing is one side. How many conductors are there in this? Three conductors. This is side 1, and this is another thing. Side 1, how many conductors? Three conductors. Three conductors are there. So this we can call as three turn. How many conductors? That number of conductors is in each side is equal to number of turns. So this can be called as a three turn, three turn coil, three turn coil. So or it can also be called as a multi turn coil. Multi means more than one. Multi turn coil. So usually we choose multi turn coils. So or generally n turn coil. So if we have n number of conductors in one side of a coil, one side of a coil. So this is other side. In this side also how many? Usually the number of conductors in each side will be equal usually. So this is, let me take the side 2 of the coil. In the side 2 of the coil, how many conductors are there? Again, three conductors. So the number of conductors present in a coil in any side of the coil is referred as the number of turns of the coil. Number of turns of the coil. Number of turns of the coil is equal to the number of conductors present in any one side. Now the thing is that we usually have this kind of coils. We usually have this kind of coils. So one side is placed in any one slot. So as like this. So this is starting. So this is side 1. So this entire coil, we are bunch of coil we are taking, and we are trying to place inside the slot. Inside the slot here. Let us say this is the slot some number. So in this slot we are placing side 1 of the coil. So let us assume this is the side 1 of the coil. Side 1 of the coil. Now the question is that where should I place the side 2 of the same coil? The side 2 of the same coil. So it can be placed either of the position, but we usually follow some trick for which. So I will tell you that where we have to place that second side. Like if I'll consider this is the slot number 1, this is the slot number 2, and this is the slot number 3, and this is the slot number 4. Then if I'll place, so this second side of the coil after in the fourth slot. See that how many slots I need to add? 1 plus 3. 1 plus 3. 3 slots. So where do we move? Fourth slot. So now let us place the side 2 of the coil of the coil in slot number 4. Now the distance between side 1 to side 2 is represented, or it is called as coil span. Coil span is nothing but distance basically. So coil span is equal to the slot number difference, that 4 minus 1 is 3. Here coil span is equal to 3. So what is this coil span basically? So the let us say that coil sides or distance between the coil sides, distance distance between coil sides is what the coil span. So distance in the sense that here just see this side 1 is placed in one slot, then where is the side 2 placed, that is referred in terms of the number of slots. So that what we call as coil span. This is what the coil span means. How much is the gap between these two, how much is the gap between these two is what the coil span. Here also you can write the same thing. So here to here is what the distance. So where the coil side 2 is placed in a slot, so that slot number represents the coil span. This is what the coil span. So which is very important. So here just let us understand these things once again by reviewing this. So we have rotor has slot and teeth arrangement. In each slot we may place some conductors, but conductors are not placed as like simple conductors. Instead of that we place a bunch of conductors which is usually framed as a coil form as like this. And to get a better higher capacity we use the multi-turn coil. So coil terminology is that a coil has two coil sides. Each side may have many number of conductors. That number of conductors in one side represents the number of turns of the coil, 3 turns coil. And the distance between side 1 to side 2 of the coil represents the coil span, and coil span is represented in terms of the slot number, how many slots are differed from side 1 to side 2. And we usually see that where do we place this second side of the coil. So that there is some technicality involved that we see little later. So now let us move on further that. So this is just, that's why I told you that this rotor arrangement is armature arrangement is little complex, but simple if you understood this generalized construction of the rotor. So I am not going much deeper, that just basic idea is that rotor is having certain core, and that core is cut into slot teeth form. In each slot we will have conductor, but that conductors how it look like is like coil. And the terminology here is side 1, side 2, starting terminal, ending terminal. And we will usually talk about the multi-turn coil. Now let us take a simple rotor as like this. So let me take the arrangement of this same thing. Let me copy this. So then let me move on here. So this is what the stator structure. Now just let me remove this portion of the rotor. I will draw the rotor again. Remaining things as it is, so no change in that. So this stator is so simple. So stator, excited field coil, etc. Those things are common. And just let me take one rotor core. Let me place over here. This is what the rotor core. And what kind of things are there here is that, so try to observe, let me write here. Stator has two poles, two poles. See this green color, north and south pole. Clear? Now, what I will do is that I will consider only one coil in which the coil is placed in these slots where the slot arrangement is exactly on the north and south pole. This is the slot arrangement, means rotor structure is made with only two slots as like this, only two slots. So now let me take the slot 1 here, it has one conductor, and now try to understand this concept carefully. If only one conductor is there, what is the phenomena? What is the phenomena? So for which, let me take this diagram, copy, and let me place beside this or under this. I will tell you why. Now consider that this conductor is carrying a current of I amperes, where current is going into the conductor, and if this rotor is trying to rotate in clockwise by certain velocity v, certain velocity v, that means the force acting is upward direction. The force acting is upward direction. The force acting on this conductor is upward direction. The force F on the conductor, I had shown only one conductor here, so is upward. And how the current is flowing? Current is flowing into the page. So this cross mark, what does it represents? Current is flowing into it. Now, so from the Fleming's this is what Fleming's right hand rule. Fleming's right hand rule. Can you tell me the nature of the induced EMF? Nature of the induced EMF. Nature of the induced EMF. Like, so let us say this is the conductor, as this conductor. So here current is going into it. Now, what will be the induced EMF in this conductor? Which side is positive, which side is negative? So that we need to find basically from these things, that is from the rotor and magnetic field, basically rotor and magnetic field. So here I had given straight away, actually the current is in this direction, but basically what is the thing is that in this way the current is unknown, the current direction is unknown. See this, force is known. Why? Because we said that assume that assume that assume that rotor is rotating rotating in clockwise, in clockwise we are externally rotating by some means. Rotor is rotating in clockwise means force should act in upward direction. We know the force, we know the flux density b direction. What is the b direction? So left to right. Now use the Fleming's right hand thumb rule, right hand rule. Find the current direction. Find the current direction. So this is, so the north to south in this direction. See here. So north to south. Now use the Fleming's right hand thumb rule. So place the thumb along the force direction and forefinger along the flux direction. Now this middle finger which shows the current through the conductor, basically FBI, if you remember. So we said that FBI from the Fleming's right hand rule. So place your three fingers, thumb, forefinger, middle finger 90 degrees to each other, and put the middle finger from north to south in this direction, and force is in upward direction. Force should be in upward direction. How does it look like? The middle finger look like it is going into the board. It is going into the board here. So that is based on this observation, based on this Fleming's right hand rule, we should decide now that the current is going into it. How we decided? Based on the Fleming's right hand rule. So if we assume rotor is rotating in clockwise, so this is one thing. So now, as I told you previously, whether it is motor or generator, we follow this FBI. But if it is generator, we talk about this I in terms of the voltage, I in terms of the voltage or induced EMF. For a generator, it need to be supplied the power. Wherever current enters to the current, that side should be the negative, other side should be the positive. So once we know the current direction, it is easy to decide the polarity of the voltage or induced EMF, E. V or E, both are same. Similarly, if we assume little bit different way as like this, let me take this entire thing again, this entire thing here. Now assume the rotor is rotating counterclockwise direction, anti-clockwise direction. Here let me write anti-clockwise direction, anti-clockwise direction. That means now rotor is rotating in this direction at a velocity of v, at a velocity of v. That means force acting on this conductor is in downward, then only it will try to, so the force here is trying to pull in downward direction. This is what the force, then only try to rotate in anti-clockwise direction. Previously the force is acting on the conductor in upward direction. This is what the force. Now we know the force, we know the force, force is in which direction? Downward direction, downward. How we decided? Based on the rotation of the rotor. We know the flux or field direction, that is from north to south, no change in the stator field direction. Now use the Fleming's right hand rule again and decide the current which is flowing through this conductor. So place the thumb downward direction, middle finger like left to right here, and see that how your forefinger left to right, middle finger is showing towards you instead of into the board, it try to show towards you. So now based on that we should say that this current is now coming out according to this Fleming's right hand rule. If you observe carefully, the current will be in opposite direction like this. It is coming out. So this coming out we can show as a dot here. Basically that we are deciding from the Fleming's right hand rule. So if the current is coming out, this is equivalent to, we can show as a conductor inside that dot. Now once we know the current direction, it is easy to find the polarity, induced EMF. So wherever current enters, that side should be negative, other side should be positive. This is what the induced EMF polarity. So these two important observations are very important. So why? Because we will be seeing so same things again and again. Clear? So these things you try to work on the Fleming's right hand rule and just yourself justify that whether you could able to find the current direction by using this Fleming's right hand thumb rule. If the force is acting upward one case, if the force is acting downward in other case, and the field direction is fixed, it is flowing from north to south, that is left to right in this direction. This is what the field direction, B, field direction. Here also B, this is what the field direction. Once we know field and force, it is easy to find the current direction. So once current direction is known, it is easy to find the induced EMF polarity. Now just let me finish last thing with this. Now what I'll do is that just let me take, instead of only one side conductor, I'll take now a coil as like this. Previously I took only one conductor here, right? So now let us assume that the rotor is rotating in some direction. It doesn't matter in which direction it is rotating. Let me choose the rotor is rotating in counterclockwise direction. Counterclockwise direction. Or even you can assume clockwise direction also. So let me choose clockwise only. So why? Because I need to change now again these force, etc. So if it is in clockwise in this way, now first try to observe, one side of the coil is placed here, other side of the coil is placed exactly under the south pole. Clear? So once it is placed under the south pole, what kind of polarity we get over here, that you need to observe. So first thing, just let me place here one conductor. This conductor is experiencing a force in upward direction. This is what the force. The flux direction is in this direction. This is what the flux or the field direction. Now what will be the I, FBI, what will be the middle finger that shows here. So if this is the FBI, so then how the thumb is pointing upward, middle finger, forefinger is pointing left to right. How your middle finger points? Middle finger points into the board, as like this. This is what the current. This is what the Fleming's right hand rule. Fleming's right hand rule. Fleming's right hand rule. So now based on this, I would like to place the current as like this. This is what, which side? Side 1 of the coil. This is side 1 of the coil. The other side is placed under the south pole, this side. See here. Now let us decide what will be that corresponding. So now this, can I say side 1, can I represent as with the cross mark? That is what we had shown already here. This one. Clear? That is the scenario over here. Now let me consider the other side under the south pole. Sorry. So under the south pole also we have one more conductor. This may be side 2 of the coil. Now here let us again interpret all these things. If this rotor structure is rotating in clockwise, then what will be the force acting on this conductor? The force should act in the downward direction on the side 2 of the coil. Then only try to rotate in clockwise, right? Like this. Then only try to rotate in clockwise like this. The force or the rotation. Now force is in downwards. What about the field? No change in the field. Field is still. So left to right. Now let us inspect what will be the Fleming's right hand rule. So thumb is pointing downward. Put the thumb downward. Put the forefinger from left to right and see middle finger, how does it look like? It look like towards you instead of into the board or page. It is coming out of the page. So now I would like to show that over here. It is coming out. How should I show? I don't know, but so you can see this. It is coming out in this way. This is what the I think this is not representing very effectively. Let me show in this way. In 3D view, it is coming out here like this, coming out of the board. So as like this. So this is what the current. Now once current is coming out of the board means, so that current should come out of this page towards you, towards me. Now this entire thing is what the side 2 of the coil, side 2, and now this entire side 2 can be represented as a conductor inside that dot. So here now I would like to show as a dot. So now try to observe the very important thing here. So let me make this entire phenomena now into the coil form, which we already taken coil somewhere here. Now let me take a multi-turn coil, this what we had shown previously. So now let me place here in place of these two. So like assume that this is what the side 1. Now I am extending the concept into a coil. First individually I took side 1, side 2. Now side 1 is equivalent to this. So what will be the induced voltage in this? Induced voltage in this, I told you already that wherever current enters, that side will be negative, other side will be positive. So here current is entering negative, positive. How much is the induced EMF? Induced EMF E is equal to B L V. And here also induced EMF E is equal to B L V. So here, so let me directly write induced EMF. So let me remove this side, etc., all those things, number of conductors, etc., and this side also. This information is now visible. Now what I'll do is that this side is positive, this side is negative. How much is the induced EMF? BLV. And other side, here is negative, here is positive. How much is the induced EMF? BLV. Now if you add up all these voltages, just see that how much is the voltage at S1 to F1 is equal to S1. Let me start here, or from F1 also, no issue. This may be negative with respect to S1, so minus. So instead of that, you can even consider in another way that the voltage between finishing terminal to starting terminal. Now it is easy. It is so BLV plus BLV, 2 BLV, 2 times of BLV. This is what the voltage induced in one coil, in one coil, voltage induced in one coil when it is rotating in clockwise direction, So like this, so we can see how much voltage will be induced in a coil. So one thing you should understand that here coil side is placed exactly under the north pole, where maximum flux is cutting by this conductor sides, and other coil is placed under the south pole. So there also maximum induced EMF is developed. If it is rotating, when it comes to 90 degrees here, this position, then the induced EMF may be completely zero. That I will talk in the next class. Okay, but try to understand up to this level how the total induced EMF in a coil, if it is a generator concept. I am talking about the generator point of view. Okay, thank you.